Welcome. In this video, we'll unravel two essential operators in C programming, the addressive operator and the indirection or dereference operator asterisk. These operators are the backbone of pointer manipulation in C. Understanding them is crucial for anyone looking to master memory management and efficient coding in C. We'll start with the basics, gradually building up to practical examples and best practices. By the end, you'll have a clear intuition for how pointers work, how to use them safely, and why they're so powerful. Let's dive in and explore the world of pointers together. Pointer is a special type of variable in C that doesn't store a regular value, but instead holds the address of another variable. Think of it as a signpost pointing to a specific location in your computer's memory. This unique ability allows pointers to play a vital role in dynamic memory management, efficient data structures, and more. Understanding what a pointer actually stores is the first step to mastering their use. In the next scenes, we'll see how to declare pointers and why they're so useful in real-world programming. Declare a pointer in C. You use the asterisk symbol before the variable name. For example, writing int asterisk p tells the compiler that p is a pointer to an integer. At this point, p doesn't point anywhere meaningful yet, it's just a variable ready to store an address. This distinction is important as using an uninitialized pointer can lead to unpredictable results. We'll soon see how to assign an address to a pointer and why initialization matters. Addressive operator, written as end, is used to fetch the memory address of a variable. For example, if you have int equals 10, then end gives you the address where a is stored in memory. This is essential for pointer assignment as you'll often want your pointer to point to an existing variable. The end operator is your tool for capturing that address and making pointers truly useful. Let's put it all together. Suppose you have int equals 10. To make a pointer point to a, you write int asterisk p equals an a. Now p holds the address of a. This means p doesn't store the value 10 but rather the location in memory where 10 is stored. This distinction is fundamental to understanding how pointers work and how they interact with memory. When you print the value of a pointer variable such as print %pp, you'll see the memory address it holds. This address matches the result of printing in a. Both represent the same location in memory, confirming that your pointer is correctly set up. Understanding this output is key to debugging and verifying pointer operations in your code. The indirection or dereference operator, written as asterisk, is used to access or modify the value stored at the address a pointer holds. For example, p gives you the value of a. Since p points to this operator is what makes pointers powerful, allowing you to read or change data indirectly through memory addresses. Once your pointer is set up, you can use asterisk p to access the value it points to. If p points to a, then p is the same as a. This allows you to read the value stored at that memory location. It's a powerful way to interact with variables indirectly, which is especially useful in functions and dynamic data structures. Pointers don't just let you read values, they let you change them too. If you write asterisk p equals 20, you're actually changing the value of the variable p points to. In our example, this means it becomes 20. This indirect modification is a key feature of pointers, enabling flexible and powerful programming techniques. It's important to distinguish between the pointer variable itself and the value it points to. The pointer p stores an address while asterisk p accesses the value at that address. Mixing these up can lead to confusion and bugs. Always remember, p is an address, asterisk p is the value at that address. See how printing p and a and p reveals their relationship. Printing p and an a both show the same address, confirming that p points to printing asterisk p gives you the value stored at that address, which is the value of a. This simple demonstration helps solidify your understanding of how pointers, addresses, and values interact in C. Proper pointer initialization is critical. If you declare a pointer but don't assign it a valid address, it becomes a wild pointer. Dereferencing such a pointer, using asterisk p when p hasn't been set, can cause undefined behavior including crashes or data corruption. Always initialize pointers before using them to ensure your programs run safely. A wild pointer is a pointer that hasn't been initialized to a valid address. Using such a pointer is dangerous because it may point anywhere in memory, leading to unpredictable results. This is why it's best practice to always assign a pointer a valid address or set it to null if it's not yet in use. The and operators are opposites in their function. The and operator gives you the address of a variable, while the asterisk operator accesses the value at a given address. This duality is at the heart of pointer manipulation in C. Mastering when and how to use each operator is key to effective pointer programming. To recap, the and operator is used whenever you need the address of a variable. This is most commonly seen when assigning an address to a pointer or passing a variable's address to a function. Remember, and is your gateway to working with memory locations directly. The asterisk operator, on the other hand, is used to access or modify the value at the address a pointer holds. Whether you're reading data or updating it, lets you work with the actual value stored in memory, not just the address. Let's walk through a practical example. Suppose you have int a equals 10, and you declare int p equals an a. Now printing p shows the address of a and printing p shows the value 10. If you then write asterisk p equals 20, a now holds the value 20. This demonstrates both assigning an address and accessing or modifying the value through a pointer. Pointers are not just about accessing values, they also make your programs more memory efficient. By using pointers, you can avoid unnecessary copying of data, especially with large structures or arrays. This efficiency is one reason why pointers are so widely used in C programming. Indirect access means you can manipulate data in one place by using its address elsewhere. For example, passing a pointer to a function allows that function to modify the original variable, not just a copy. This is a powerful technique for writing flexible and efficient code. As you work with pointers, you'll start to develop an intuition for how memory is organized and accessed in C. This understanding is essential for tackling more advanced topics like arrays, strings, and dynamic memory allocation. The more you practice, the more natural pointer manipulation will become. Pointers are closely related to arrays in C. In fact, the name of an array acts as a pointer to its first element. This relationship allows you to use pointers for efficient array manipulation and traversal, making your code both faster and more flexible. Strings in C are arrays of characters, and pointers are often used to manipulate them. By using pointers, you can efficiently process, modify, and traverse strings, which is essential for many real-world applications. Dynamic memory allocation in C relies heavily on pointers. Functions like malloc and free use pointers to manage memory at runtime, allowing your programs to handle data whose size isn't known in advance. Mastering pointers is essential for working with dynamic memory safely and efficiently. To use pointers safely, always initialize them before use, avoid dereferencing null or wild pointers, and free dynamically allocated memory when it's no longer needed. These habits will help you prevent bugs and memory leaks in your C programs. Some common mistakes with pointers include forgetting to initialize them, dereferencing invalid addresses, and not freeing memory. These errors can lead to crashes, data corruption, or memory leaks. Being aware of these pitfalls is the first step to avoiding them. A null pointer is a pointer that doesn't point to any valid memory location. Setting a pointer to null is a good way to indicate that it's not currently in use. Always check for null before dereferencing a pointer to avoid runtime errors. Pointers can be incremented or decremented to move through arrays or memory blocks. For example, if p points to an array, p++ moves to the next element. This arithmetic is based on the size of the data type the pointer refers to, making pointer arithmetic a powerful tool for efficient data processing. Passing pointers to functions allows those functions to modify the original data, not just a copy. This is especially useful for returning multiple values or working with large data structures efficiently. Understanding how to use pointers in function arguments is a key skill for C programmers. Pointers can also point to structures, enabling dynamic data structures like linked lists and trees. By using pointers, you can create complex and flexible data models that are essential for advanced programming tasks. Function pointers are pointers that point to functions instead of data. They allow you to write flexible code such as callback mechanisms or dynamic function selection. This advanced use of pointers opens up new possibilities in C programming. If you allocate memory dynamically but forget to free it, you create a memory leak. Over time, this can exhaust your system's memory. Always pair every malloc with a corresponding free to keep your programs efficient and safe. Pointers are often used in recursive functions, especially when dealing with dynamic data structures like trees or linked lists. They allow functions to traverse and modify complex structures efficiently, making recursion more powerful. In C, file operations often use pointers such as file *fp. These pointers are used to manage file streams, enabling reading from and writing to files efficiently. Understanding how pointers work is essential for effective file handling. Linked lists are a classic example of pointer usage. Each node contains data and a pointer to the next node. This structure allows for dynamic memory allocation and efficient insertion or deletion of elements. Dynamic arrays in C are created using pointers and dynamic memory allocation. This allows your programs to handle arrays whose size can change at runtime, providing flexibility and efficient use of memory. A double pointer is a pointer to a pointer. In C, this is written as int pp. Double pointers are used in advanced scenarios such as dynamic multidimensional arrays or passing pointers by reference to functions. In C, command line arguments are handled using pointers. The main function receives arguments as int arg char argv, where argv is an array of pointers to strings. This allows your program to process input flexibly and efficiently. Functions like malloc, calloc, and realloc return pointers to dynamically allocated memory. Understanding how to use these functions and how to free memory with free is essential for writing robust and efficient C programs. Sometimes, you may need to cast pointers from one type to another, especially when working with generic data structures or memory buffers. Always ensure that your casts are safe and meaningful to avoid undefined behavior. You can use the const qualifier with pointers to prevent modification of the data they point to. For example, const int p means you can't change the value at p, but you can change where p points. This adds safety and clarity to your code. The volatile qualifier tells the compiler that the value pointed to by a pointer may change unexpectedly, such as in hardware programming. This prevents the compiler from optimizing away necessary reads or writes, ensuring correct behavior in special scenarios. When you have a pointer to a struct, you use the operator to access its members. For example, p_member is equivalent to *p_member. This syntax makes working with structures via pointers more convenient and readable. Functions in C can return pointers, allowing you to return dynamically allocated memory or data structures. This is a common pattern for creating and managing complex data in your programs. Pointers can be used to work with multidimensional arrays, allowing you to create flexible data structures and efficient algorithms. Understanding how to navigate these arrays with pointers is an advanced but valuable skill. Wrap up: always initialize your pointers, understand the difference between what they hold an address and what they access *p, and use the and operators correctly. Mastering these basics will help you write safer, more efficient, and more powerful C programs. With practice, pointers will become a natural and indispensable part of your programming toolkit.